Hi, I'm Jeff Groh, and this is Calculus 1. Today we're going to talk about optimization. These typically have the following form. We're trying to find the maximum or minimum values of some function, and in this class, a function of two independent variables, x and y. But this will be subject to some kind of constraint. The constraint will take the form of a function equal to, say, 0. You can always have, if you have an equation, you can always move everything to one side and get 0 on the other. When I have an equation of this form, I can freely choose one of the two variables, but the other variable will have a value determined by the equation itself. So if I choose x, y then is determined by the equation. You can see that I have 1 degree of wiggle room in a two-dimensional space. That means I end up with a one-dimensional object, a curve, in R2. We're trying to find the maximum and minimum values of this function subject to being on some curve. There's a context in which I use something as kind of a generalization of this, a little bit higher dimensions. When I was getting ready to go to graduate school at Idaho State University, I realized that I was going to be quite poor. They were willing to pay me $4,500 for 10 months. That means $450 per month in exchange for teaching a class each semester. Well, I knew this was going to be very difficult to survive on, so I found an apartment, a basement apartment, for $120 a month, which was great. Very difficult at the time to find apartments anywhere where I was from for less than $400 a month. Finding a basement apartment for $120 was fantastic. But there were only a few other places where I could economize. Fortunately, the cost of heating was not very high in Idaho at the time. They got a lot of hydroelectric and nuclear power in that area, which was very cheap at the time. My electric bills amounted to about $7 a month. Food was one of my major expenses, and so I needed to economize on food. Knowing this, I went to the grocery store and I priced a number of different foods that I felt like I could eat. At the same time, I bought a nutrition almanac and looked up the constituents, nutritional constituents of these various acceptable foods. Then, I programmed my calculator to solve the following optimization problem. I needed to find the minimum cost. I had more than two variables because each of the variables represented an amount of some acceptable food. And so there were many acceptable foods, which means I had to deal with something in pretty high dimension. The cost function was the price per unit times the number of units for each food. As you can see, that won't have any minimum or maximum if left on its own. You have to have some kind of constraint. The constraint arose because I need to get the various nutrients that my body needs. So I programmed the calculator for all of those nutritional requirements and how much of those nutritional requirements were provided by these various acceptable foods. This was in 1989, and I used a calculator that I had purchased in 1986. This was an old calculator and it ran very slowly. In fact, it ran this program that I wrote for 20 minutes. I was really quite concerned that it might run out of batteries in that 20-minute time frame, and I might not get an answer. But when it did finally come to a stop, it told me that I needed to eat. For a minimum cost diet, providing the various nutrients that my body requires, I needed to eat beans and rice. Yes, beans and rice, I know. anyone could have told me this. I didn't need to program a computer, but I did. And it gave me the answer. There were a few other things that were required, a little bit of multivitamin mineral, a little bit of spinach, things like that. And the rice had to be brown rice in order to get the optimal nutrition. In any case, yes, you'll never know when you might need to use one of these constrained optimization problems. So let's get to some examples. For example, suppose that a farmer has a barn. The barn wall is right here, and he has 500 feet of fencing and wishes to enclose 4 pens next to the barn. So the barn goes in this direction, and 4 pens are constructed next to the barn with fencing, and there's a limit though, 500 feet of fencing. Find the dimensions of the pens so that the pens are as large in terms of area as possible. As large an area is enclosed by these pens as possible. So, to solve this problem, we're going to first define some things that are variables here. This is a very important step. You need to define variable names to the unknowns in the problem. In this case, we have x and we have y. Each of these is also x. And if we make 4 pens, there are going to be 5 lengths the size of x, and 1 the size of y. We'll assume that we don't need to enclose this side because it's next to the barn. So we need to maximize the area which is x times y, but that is subject to a constraint. The constraint is 5x plus y is equal to the amount of fence that is available, 500 feet. Notice here we're trying to maximize a function that involves 2 variables. That's a problem for us. In all of the problems that we've seen to this point, where we're looking for a maximum on some function, that function has had only 1 independent variable. This function has 2, x and y. The constraint allows us to eliminate one of those 2 variables, and then we'll have a function involving only 1. So in this case, we can use the constraint to solve for y, and then substitute into the area formula. Then we'll try to figure out where the maximum is for that function. The area function, after we substitute, is going to be x times, if we move this 5x over, y can be replaced by 500 minus 5x. So the area function is going to be 500x minus 5x squared. You can see that this will be a parabola opening down, so it will in fact have a maximum. To figure out where that maximum is, a parabola opening down, we need to calculate the derivative, set it equal to 0, and solve for x. That will be a critical point of the area function. Calculating the derivative, we get 500 minus 10x. If that's set equal to 0, you can see that x has to be 50 feet. So that gives us the depth of each of those pens. How about the width of the entire set of pens? The width, as you'll recall, is determined by y equals 500 minus 5x. If we plug in 50 for x here, 5 times 50 is 250. 500 minus 250, y is going to be 250 feet, which means this is one big barn. On this next problem, Suppose that we are given a rectangular sheet of cardboard. About this piece here. And let's suppose that it's 24 inches this way and 36 inches this way. We would like to cut little corners out, the same amount on each corner, so that we can flip up these little tabs and form a box. How much should we cut? We'll name that variable x. How much should we cut in order to obtain a maximum volume? You can see that the volume here of the box that results will have a height of x. The width, though, is not going to be 24. It's going to be 24 minus x on this side and also minus x on the other side. That's 24 minus 2x. And in the other direction, it's going to be 36 minus 2x. We need to maximize the value of this function. To do that, we need to take the derivative, set it equal to 0, and solve for x. To calculate the derivative, we might use the product rule. The derivative of the first is 1 times everything else. Plus x times the derivative of the second, which is negative 2, times the last. And then plus the derivative of the last factor is negative 2 times x times 24 minus 2x. Next, we need to solve this equation for x, so let's boil everything out and simplify. We'll have 0 equals, on this first part, we're going to have 24 times 36. There is an easier way to do this. 36 is 3 times 12, and 24 is 2 times 12. You end up with 3 times 12 times 2 times 12, that's 6 times 12 squared. 12 squared is 144, and if we multiply that by 6, we get 600 plus 240, that's 840, plus another 24, that's 864. It's usually better to multiply backwards. So we'll have 864, and then minus 48x minus 72x, and then plus 4x squared. Down here we'll distribute minus 2x to both terms. We'll have minus 72x plus 4x squared, and then we'll have minus 48x plus 4x squared. The x squared terms add up to 12x squared. What is 72 and 48? 70 and 40 is 110, plus another 10 is 120. We'll have another pair like that too. That's minus 240x, and then plus the constant 864. What can be factored out? 12 goes into 240 and into this. Does 12 go into 864? Well, yeah. It was 12 squared times 6. So 12 can be factored out of this whole thing. We'll get 20x, and plus, if you think about it, if you take a 12 out, all that's left is 6 times 12. That's going to be 72. By the zero product theorem, we can cross off the 12, and we can solve the rest using the quadratic formula. X equals minus b plus or minus square root b squared. Negative 20 squared is 400. Minus 4 times 1 times 72. All over 2a. So 4 times 72. 4 times 70 is 280. And then we'll have another 8. So that's 288. 400 minus 288 is 112. So we'll have 10 plus or minus a half times the square root of 112. Let's see, what can we bring out of the square root from the 112? Well, 4 goes into that. 4 goes into 11 twice with a remainder of 3. 4 goes into 32 8 times. Anything else come out? Well, isn't that 4 times 7? So it looks like 112 is 4 times 4 times 7. So it's 4 squared times 7. We can bring the 4 out. Leave the 7 and bring the 4 out. This leaves a 2 out here. So we get 10 plus or minus 2 root 7. So which value of x is it? The plus or the minus? Notice that the square root of 7 is bigger than 2 but smaller than 3, because 3 squared is 9 and 2 squared is 4. So whatever this is, it's 2 root 7 is going to be bigger than 4 but smaller than 6. Okay, but 10 plus something bigger than 4, that would be bigger than 14. But wait a minute. Remember, if you're cutting, x is the amount that we're cutting out of the corners. This was 24 by 36, as you might recall. You can't cut more than half the way across, and half the way across would be 12 inches. So it can't be plus. It must be minus. You can't be subtracting more than 6, so this will be positive. And so this will tell you how much to cut the corners in order to achieve a box having maximum volume. In our next example, we're going to answer the question, which points on the parabola y equals 9 minus x squared are closest to the point 0, 3. To get a picture of what this looks like, our parabola is some curve that opens up like this, and we have this point 0, 3 on the curve, 0, 3 on the y-axis. Which of the points on this parabola are closest? If we do have a point on this parabola, it will have the form x 9 minus x squared, because the y-coordinates are constrained to be on this curve. What is the distance between here? We need to know how to calculate that distance. The distance is given by the square root of x minus 0 squared plus 9 minus x squared minus 3 squared. We want to minimize this distance, which is a complicated thing. This crazy expression has all kinds of, it has a square root and these squares. It seems more complicated than what I really want to deal with. So what I'm going to do instead is I'm not going to minimize the distance, I'm going to minimize the distance squared. When I square this, I'll leave it like this for now. This is the expression that I'm going to calculate the derivative of. That will avoid some ugly complications involving square roots. I'll calculate the derivative now and set it equal to 0. The derivative of the first term is just 2x. Over here I'll use the chain rule. I'll bring the power down, leave the inside alone, but then I have to multiply by the derivative of the inside, which is negative 2x. You can see that we can factor a 2x out. I'll have to leave the minus and this too. The rest of this will simplify. 9 minus 3 is 6, and then we still have a minus x squared. You can see that x equals 0 is going to be a critical point. To find the other critical point, we need to set the other factor equal to 0. But before we do that, let's rewrite this as positive 2x squared. We'll have a minus 12 plus 1 is minus 11. Moving this over and divided by 2, we get x squared is 11 halves. Taking the square root, we'll have plus or minus the square root of 11 halves. Let's not worry about rationalizing the denominator here. This gives us 2 more critical points. Now, which of these gives us a maximum, if any? To find out, remember this was our derivative, we'll plot our critical points. Plugging points within each of these 4 intervals into the derivative will determine which of these is going to be a local minimum and which a local maximum. If we plug in something very, very negative, notice this is going to be a 2x squared minus 11 after we simplify it. If x is very negative, you square it, it becomes quite positive, but you're still multiplying by a negative here, which means our function is decreasing to this point. What happens in here, say at negative 1, we'll get a negative here. Negative 1 squared is 1, times 2 is 2, minus 11 is negative. Negative times negative is positive. We have a local min in this location. When we plug in something like 1, we get negative times positive, which is negative. That makes 0 a local maximum. And then we'll get a positive over here, so again we have a local minimum. That means the minima will occur when x is plus or minus the square root of 11 halves. What are the y values? Remember the function was 9 minus x squared. If we plug this in, we'll have 9 minus 11 halves. This is 18 halves. 18 halves minus 11 halves is 7 halves. These points will give you minima for the distance. On our next problem, we're we're told that a demand function is given by p of x equals, let's say, 77 e to the negative 0.123411x. Negative 0.000011x. A demand function, by the way, is the price per unit at some level of production. X is the number of widgets that have been produced and sold. A widget, by the way, is just a generic name for any product that you wish to sell. So if we've produced X widgets and sold them, the price per widget will be this many dollars per widget. That price per unit will depend upon how many units we've sold in many cases. We're going to find the value of X that maximizes revenue. The thing about revenue is the price per widget times the total number of widgets. It's X times P of X. And we want to find the value of X that gives us a maximum for this function. First, let's rewrite what the revenue function is. Now, we need to calculate the derivative of the revenue function, set it equal to 0, and solve for X. To calculate the derivative of the revenue function requires the use of the product rule, since we have X here and then another X over there. Using the product rule, we'll have 77 times e to the negative 0.123411x plus this times the derivative of the next part. The derivative of the next part requires the chain rule. And so we'll get minus 0.123411, that's the derivative of the exponent, times e to the negative 0.000011x times the other factor, which is 77x. We can factor the e to the power out and cancel it off, because that is never equal to 0. You can cancel the 77 off. That leaves just 1 on this term. It follows that x, if we move this term over, we'll have a positive small number times x equals 1. So it'll be 1 divided by 0.123411. How much is that? That's approximately 90909.09, etc. If we're rounding to the nearest whole widget, that's going to be about 90,909. This is the level of production that gives you the maximum revenue. You don't normally want to maximize revenue. Normally you want to maximize profit. However, there may be situations where you need cash flow, so you may just need the revenue. On our next problem, we're going to consider what happens if we have a dog and this dog can run at 4, let's say, it's just relaxing, 4 miles per hour. And here's the shore, a beach. And here we are, standing right here. This is where we're standing, and we have a ball. We're going to throw that ball, and our dog, Fido, is right next to us here. This is Fido. We're going to throw that ball, and we're going to throw it into the water. Now, the dog, I suppose, starts out, here's Fido, he's going to start out, let's say, 20 feet from the shore, and he's going to be about 50 feet from where the ball is parallel to the or perpendicular to the shoreline here. He's going to be about 50 feet from where the ball is perpendicular to the shoreline here. Now, let's suppose that Fido, and this is how fast he can run, 4 miles per hour, but he can only swim at 1 mile per hour. So he's much slower swimming. So it's better for him to cover most of the distance on the shore and then swim the remaining distance. What I want to know is, how far down the beach should Fido run before jumping into the water and swimming the remaining distance in order to minimize the amount of time it takes to retrieve the ball? So we're trying to minimize the total time. Keep in mind, distance is rate times time, so that time is distance divided by rate. We have two distances here. We have this distance, and we have two rates as well. So the total time is going to be time 1 plus time 2. Time 1 will be the time that the dog runs along the shore, and time 2 will be the time it takes for the dog to swim. Time 1 is going to be this distance divided by 4. That distance will depend upon the value of x. Here we have a right triangle. We'll put the dog here. Have a right triangle, and d1 is the length of the hypotenuse. This side is 20, this side is x. So d1 is going to be the square root of 20 squared plus x squared, which means t1 is going to be this divided by 4. d2 will be this distance, and again we have a right triangle, but this distance here is going to be 50 minus x. And let's suppose there's one more variable that we haven't defined, and that is how far into the water we've thrown this ball. Let's suppose that that's 10 feet. In that case, d2 is going to be the square root of 10 squared, or 100, plus 50 minus x squared. t2 is going to be d2 divided by 1. Now, the units are a little off here. These are measured in feet. 4 is measured in miles per hour. But I think you'll see that we could multiply each of these by a conversion factor. When we add them together, the conversion factor can be factored out and canceled off. The total time, the thing that we're now trying to minimize, is the sum of these two things. 1/4, I'll write this as 400 plus x squared to the power 1/2, plus, and we'll write this as 100 plus 50 minus x squared, all to the power of 1/2. To minimize the total amount of time it takes for Fido to retrieve the ball, we need to calculate the derivative of the total time with respect to x, set it equal to 0, and then solve for x. I hope you're realizing that this must be one hyper-intelligent dog. When we take the derivative, we'll bring this power down, leave the inside alone, and subtract 1 from the exponent. but we need to multiply by the derivative of the inside, which is 2x. Similarly over here, 1/2, 100 plus 50 minus x quantity squared to the negative 1/2, and then the derivative of the inside. That's going to be twice 50 minus x to the power 1, and then times a negative 1 after that. Okay, you can see that we can cancel some things. Also, this term is negative. Let's take this whole term and put it on the other side of the equation. That will give us a positive. Rearranging the equation, we get 50 minus x over the square root of 100 plus 50 minus x quantity squared equals x over 4 times the square root of 400 plus x squared. Now, we could try to solve this the old-fashioned way. We can square both sides and then cross multiply, gather all the terms onto one side, and then solve for x. But I have another way I'd like to show you. I thought I'd show you how to use a computer algebra system like Maple to solve this. We're going to solve, let's see, what was it? 50 minus x divided by the square root of 100 plus the quantity 50 minus x quantity squared equals x divided by 4 times the square root of 400 plus x squared. And we're going to solve that for x. But in order to do that, I'm going to find the floating point solution. And it tells me the answer is 47.63. So the dog should run 46.63 feet down the beach and then jump into the water and go towards the ball. That gives the shortest path in terms of the total amount of time taken for the dog to retrieve the ball. People have actually done this experiment, and they wanted to see how well the dog was able to match the theoretically best answer, and the dogs do reasonably well. There have been articles published on this, believe it or not. On this next problem, what are the dimensions of the open top cylindrical can of least surface area that contains or that has a volume of 512 cubic centimeters. The picture is like this. We have a can. It has the sides, it also has a bottom, but it doesn't have a top. I want to have the smallest total surface area on this can, but it has to contain 512 cubic centimeters. We're trying to minimize surface area. If this is some radius r, and this is a height h, the surface area on the side is 2 pi r, this is the distance around, times how far you sweep it, 2 pi r h. That results from something called the Theorem of Pappus. If you have a curve of length L and you sweep it at a right angle some distance h, the surface area of the region swept out is L times h. But we also have to add the area of the base, and that's going to be pi r squared. We want to minimize the surface area. The function you're trying to minimize is called the objective function. In our case, the objective function has two variables, r and h. That's a problem. We've been able to only maximize and minimize functions of one variable, and we won't teach you how to maximize or minimize functions of more than one variable until Calculus 3, multivariable calculus. In this case, we need another constraint. Fortunately, we already have one. The volume is supposed to be 512 cubic centimeters. The volume can also be calculated from another variant of the Theorem of Pappus. If we take the area of the base and multiply it by how far we sweep it, we end up with the volume. The volume is pi r squared h. This provides a constraint on the two variables. We can solve for one of the variables and then substitute into the equation above. In this case, let's solve for h. H is going to be 512 divided by pi r squared. We'll substitute that into the original equation. The surface area formula is now 2 pi r times 512 divided by pi r squared plus yet another pi r squared. We can simplify this a little bit. We can cancel pi off. We can cancel one factor of r off, and then multiply 2 times 512. The first term is just 1024 divided by r, and the second term is still pi r squared. Now we have a function involving only one independent variable. To find the minimum value, we'll just take the derivative, set it equal to 0, and solve for r. Taking the derivative, remember the derivative of 1 over x is negative 1 over x squared. So here we're going to have negative 1024 divided by r squared. And then plus 2 pi r. Setting this equal to 0, we need to move this term over. That gives us 1024 divided by r squared is equal to 2 pi r. We'll need to take the 2 pi and divide it off and multiply the r squared over. This gives us r cubed is 1024 divided by 2 pi, or 512 divided by pi. Taking the cube root, r is the cube root of 512 over pi. Now, 512 is 2 to the power 9, and 2 to the power 9 to the power of 1/3 is going to be 2 to the power 3, or 8, divided by the cube root of pi. This will be measured in centimeters, and that's the radius. But we're still missing something. We need the height. I said, what are the dimensions of the can? The dimensions will be defined by the radius and the height, h. So, the height is 512 divided by pi, r squared. 8 squared is 64, and the cube root of pi squared is pi to the power of 2/3. 64 goes into 512 how many times? Well, keep in mind, this is 2 to the power 9, and this is 2 to the power 6. You subtract exponents, you get 2 cubed, or 8, divided by pi to the 1 divided by pi to the 2/3, you subtract the exponents. 1 minus 2/3 is 1/3. And so you get 8 divided by the cube root of pi in centimeters for the height as well. So the height of the can is equal to the radius. The diameter will be twice the height. That will give you the maximum volume. I hope you enjoyed thinking about these optimization problems today. You start with the max or the min of some objective function. Typically, the objective function will have two variables. If the objective function only has one variable, you can proceed with the maximization problem right away. Take the derivative, set it equal to 0, solve for the variable. Otherwise, you'll need some kind of constraint, which is in the form of an equation involving those two variables. This is a subject called constrained optimization. In Calculus 3, we'll have a special method called Lagrange Multipliers that will apply in a multivariable case. In the subject operations research, which is the applications of mathematical techniques to solve business problems, there's a special method for linear objective functions and linear constraints called the simplex method. That's the method that I programmed when solving my diet problem when I was headed to graduate school.